good afternoon. So let's continue for the afternoon session. So for me, it's a pleasure to present Juan Carlos Mongez from USP, São Paulo. He is going to talk about on the finiteness of measure of maximal entropy for certain partially hyperbolic diffeomorphisms.
Thank you. I would like to start by thanking the organizer for the invitation. It's so special for me to be here in the Brazilian School of Dynamical Systems. And it's even more special for me because today is taking place in UFRJ. That was my home for 6 years. So it's very nice. And I would like to say something about Palis, Jacob, that I didn't meet him personally, but I know that one of the reasons that I can be a mathematician here in Brazil is because the time and the energy that he spent to create this great community. So thanks to Pali for his legacy. Well, now I'm going to speak about my work that is a work in collaboration with Pacifico and with Mauricio, some new results. And well, as an introduction, let's recall what is a measure of maximal entropy. That is the thing that I'm going to speak about today. Well, in dynamic, we have two types of entropy, the topological entropy and the metric entropy. The metric entropy is related to an invariant measure, and they are connected by the variational principle. We have that inequality, and an ergodic measure that achieves this supremum is called a measure of maximal entropy. So the question is, when does diffeomorphisms have finite measure of maximal entropy? And this question is important because sometimes we want to study our system using ergodic theory. But the problem is that sometimes we have a lot of invariant and ergodic measures, and we have to choose one to focus on because there are infinitely, we have a lot. And the measure of maximal entropy are the measures that capture all the complexity of the system. So they are a good candidate to apply the theory that we have in ergodic theory and take information about our diffeomorphisms that could be important to understand it better. Well, we want to study diffeomorphisms, and the question is, how do we know until now? And we know that when we put hypothesis over the regularity or over the dimension of the manifold, we can get finitely many measures of maximal entropy. But that is true in dimension 2 and for the infinity diffeomorphism. That was proved by Newhouse and Busi-Krovizer-Sari. And if we take off this hypothesis, we can find example with any measure of maximal entropy or with a lot of them, with infinitely many measures of maximal entropy. But if we don't want to put hypotheses in that direction, we can ask for uniform hyperbolic diffeomorphisms, and we are going to get the result that we want. So this is the type of system that we want to focus on and try to extend that results for more general diffeomorphisms. So here we have the partially hyperbolic diffeomorphisms that are a natural generalization, but in this time we have three directions. We have the stable and the unstable direction, and now we have an intermediate direction when we don't know what is happening exactly, but we have a domination. That means that it's never stronger, the contraction or the expansion. In the case that happens, is never stronger than the stable and unstable direction. Well, it's easy to find examples with infinitely many measures of maximal entropy, even in the case of partially hyperbolic diffeomorphisms. So we need to put some hypotheses in this type of systems to find the result that we want. And so now I'm going to introduce an open set of partially hyperbolic diffeomorphisms that admit finite measure of maximal entropy. But for that, I have to introduce this definition that maybe look a bit complicated, but the idea is that when you have a partially hyperbolic diffeomorphisms, you have the unstable direction and there's the unstable band. And this is integrated by the unstable folation, and each folation that is for each point you have an unstable manifold. Here you can see how the dynamic expands distance along the unstable manifold. So in this unstable manifolds, we have entropy, and so we can calculate the unstable entropy along each unstable manifold. And at the end, we can take the supremum. Take the supremum over that, all that entropies that comes from a stable manifold. Of course, there is some technical things, but this is the philosophy behind the definition. And well, when you have a map, a partially hyperbolic diffeomorphisms, and you take F inverse, the stable direction becomes the unstable direction, and so you can define the stable entropy as the unstable entropy of F inverse. This definition is interesting because this is an alternative definition for the case of uniform hyperbolic diffeomorphisms. Of course, in the case when you see a partially hyperbolic diffeomorphisms, the stable entropy is always less or equal than the topological entropy. But the reason of that definition is because when you calculate the unstable entropy, you are taking the entropy that comes from the uniform part of your partially hyperbolic diffeomorphism. So it's taking the more regular part of the entropy, and that allows you to get properties that you don't have for the general entropy, but you have for the unstable entropy. And well, now I can introduce our first theorem. Of course, the first step is to study what is happening when the central dimension when the central direction have dimension 1. And in this context, we have to ask for a bit of regularity, just see a bit more than C1. The manifold could be anything. Well, have to be closed, compact, boundaryless. And so for this context, if we put the hypothesis that the topological entropy is greater than the unstable entropy, so we are going to get an open set in the C1 topology such that each diffeomorphism has finite measure of maximal entropy. So in a neighborhood, we have always finite measure of maximal entropy. But more interesting even is that in that neighborhood, it's impossible that the number of measures of maximal entropy increase. I mean, when you have the uniform case, you know that the number of measures of maximal entropy is locally constant, but in this case, we can find a bounded above. And the reason that we can't get the result of the uniform case is because in that case, all the uniform diffeomorphisms are conjugate. I mean, they are almost the same. But in this case, that is not true, and we have to deal with this problem using other techniques, and for that, we can get the equality. We don't know if it's possible in general to guarantee that it's equal. And if you want to get the uniqueness, we have other result that the general setting is the same, central dimension 1, and a bit of regularity. In this case, with the same hypothesis, but putting that the stable manifold have to be minimal. Minimal means that each stable strong manifold is dense in the manifold. So the stable manifold are dense along into the big manifold, the manifold M. In this case, we have a neighborhood, again, in the C1 topology, such that each C1 diffeomorphisms admit just one measure of maximal entropy. So we have the case of finiteness, we have the case hypothesis to guarantee the uniqueness, and the next step is to see what is happening when the central dimension have dimension 2. In this case, we need to put one more hypothesis that is that the central direction that have dimension 2 admit that the composition into two one-dimensional bundles, and they are dominated. Dominating again means that we have a control about the strong that they are contracting or expanding in each point. When we have this hypothesis, we ask now that the topological entropy is greater than the unstable and the stable entropy, and we get the same result. Again, open neighborhood where each diffeomorphism has finite measure of maximal entropy and the number is bounded above. But the reason for that, for what these things work, is because when you have a splitting, a stable, a strong stable direction, central direction, and unstable direction. Suppose that you are in the case of central dimension 1. That is the easier one. When you have this, and you try to see the entropy here, and this guy is not achieving the entropy, so that means that this guy have to help this guy to expand the orbit, to create more and more orbit. And if this is happening, that means that a lot of points here have to expand distance in certain way. The idea is that the entropy is not coming from here, so the central direction has to help this guy to achieve the topological entropy. And so this is the reason for why this guy is something more close to this guy than to this guy. Nice. So a way to formalize the thing that I said is using hyperbolic measure. So a hyperbolic measure is an ergodic measure such that all the Lyapunov exponents are far away from 0. I mean, you know that they are not 0, the Lyapunov exponent. And in our context, there exists key, a positive number, such that all the measures of maximal entropy in that neighborhood are key hyperbolic. So they have a good behavior in that neighborhood, not necessarily a uniform behavior, but for the important points, I mean, for the points that are creating entropy, they behave in rate in a good way. So this is the type of examples that we can get for partially hyperbolic diffeomorphisms, but we also can create a new family where we have finite measure of maximal entropy. For that, we use the skew product. So think about one of the examples that we have. Anything, theorem A, B, or C. You can choose. And so take that key that we have in the last lemma. So you can take that map G such that for each point in the manifold, you have a diffeomorphism in the circle. And you are going to ask something about your diffeomorphisms, that this is this inequality that depends of that key. When you have that, you can define this skewed product, the big F. We have a small f that is a guy like in the theorem ABC. And so we define a new map that is big F, that is a skew product. And so if we take the projection over this first coordinate, meaning over M, we are going to take a semi-conjugation between this map, the skew product, and the base. We call base the map small f. This is the base, and the other maps are in the favor. And so this is a semi-conjugation. And it's interesting because as the new manifold that we put here is a circle, there is not a space to generate entropy. So this map have the same entropy of this map. And the reason is because they are circles. And even more important is that we can create a map between the measure of maximal entropy of the skew product This is a map that, so for each ergodic invariant measure here, you can project over a measure here. And for the same reason, the entropy is preserving here. If you take tilde mu and you project over mu, the entropy, the metric entropy with respect to the skew product is equal to the metric entropy of this guy. So that things are preserving. And other thing that is interesting about SQ product is the definition of F. This guy just depends of the first coordinate, just doesn't depend of the second one. So the first coordinate doesn't depend on the second one. This is something good. And well, our result says that we can find a family, a very big family, CR open and C1 open and CR dense, such that each diffeomorphism here have finitely many measures of maximal entropy. Of course, we are in the, I forgot to say that we are in this family. Recall that this property is an open property. It's open in a C1 neighborhood. So we can define this family, where the first coordinate is as in the theorem A, B, or C, and the second coordinate is in this way. So for this family, we can find a very big set where the things work. And well, I would like to speak now about the proof of this theorem. So the first thing that I need to introduce is the stable holonomy. So when we have hyperbolic measures are important because they say that the things works in a certain way, like in the uniform case. It's not exactly that, but it's something close to that. And that means that for each point, for almost every point, when you have a hyperbolic measures, you have a stable manifold, a stable Pessin manifold. A stable Pessin manifold means that the points are going to converge exponentially fast along the orbit. But well, using that manifold, we can define the stable holonomy. Well, suppose that you have a stable manifold. Suppose that is a stable manifold of a fixed point, to be easier. So here you have X, you have Y, and you have the fiber, that is a circle. Suppose that this is a circle. So this is other circle. And you want to connect these two maps. Here you have a map GX, and here you have a map GY, and you want to connect them, this dynamic. So you know that these guys are going to converge. They will be so close in the future. So a way. So we use this property that they are going to be close to define this limit. And as they are converging so close, we can prove that you can jump for one dynamic for the other one in a continuous way. And this is the main thing about how holonomies works. So we have that this map that composition that is along the orbit. Pay attention. It's important to know that this stable manifold is with respect to small f, with respect the base, and not with respect the big F, the skew product. So now that we know this, what is holonomies, we can use that holonomies to define two very important definitions that are pinching and twisting. Okay, we have F small f, the base, and we know that they have finitely many measures of maximal entropy. So for each measure of maximal entropy, we are going to take a hyperbolic periodic point that is related to this measure. This definition of relation, this one, doesn't matter, don't worry about that. The point is that this hyperbolic periodic point is related for certain reason with this measure. And the point is, if this map that depends just on the periodic point, it's a Morse-Smale or not. Recall, Morse-Smale means the no-boundary set is just hyperbolic periodic points, and they are finite. So that is the question. The question is, I'm taking a hyperbolic periodic point for the base and taking the map. Suppose that this is a fixed point. So the question is if this guy is Morris male. This GX. This is the question. And now that we know that suppose that is pinching, the next question is what is happening with some homoclinic intersection, transversal homoclinic intersection. What is this? Well, when you have a hyperbolic periodic point that is related to a measure of maximal entropy, in this case, we have transversal homoclinic relation. This is the stable manifold, this is unstable manifold, this is Pj, and this is Z. I'm talking about the second property, the property in twisting. This is Z, G, J. The question is, we have the fiber here, and we have this fiber. If we use the holonomy, now the unstable holonomy, we can walk along this path. We can walk in this way. And now that we are in ZJ, we can come back to PJ. And so the question, I can't use my hand, so the question is, I think that is impossible. So the question is, if when you are walk along that cycle, this cycle, if when you come back using the periodic points, if they are gonna be preserving, you have your points, they are gonna walk along the cycle, and the question if they are preserving, if they are gonna coincide, one of them, just one of them. If that doesn't happen, we say that our system is twisting. And the main thing with this, well, one of the things about these two properties is that they are open, C1 open and CR dense. For what reason? Well, when you take your hyperbolic periodic point, if this guy is not a Morris male, we know that Morris male are dense, open, so you just have to change the map. And you can do that because the hyperbolic periodic point just depends on the first coordinate. So you can change just this map, and you are going to preserve the hyperbolic periodic point, but you are going to change this map. And so for that, you can make that perturbation easily. And the reason for that the twisting is open is almost the same. The thing is that this guy is an isolated guy when you take the orbit. This orbit is going to come from here, and when you take F inverse, it's going to go until here. And for that, this point is isolated when you see the dynamic of small f, of the base. And so you make here a perturbation. You can take G, Zj, tilde, and define something like the whole map that is preserving the hyperbolic periodic point and put a small rotation. And so that rotation is going to break that preservation. It's going to break how the points are going to coincide. So these properties are so common in our family, are very, very, very common properties. And well, but this is important because this is related with the invariational principle by Avila-Viana and using a coding theory by Saric and Ovadia, we can prove that for all the measure of maximal entropy, the Lyapunov exponent is far away from zero. So we have the same case that before. Central Lyapunov exponent that are the problem are very good. Now this beta depend on the map F, but for that map we have a good beta. So let me see my time, 6 minutes. Okay, so now I would like to say why this Lyapunov exponent be far away from zero, it's important. Why this is a good thing? I know that it's something close to uniform hyperbolicity, but maybe it's not as good as we want. But it's very good. And the reason is because we have hyperbolic time. What means? Look at that set. That set is saying that you have a R that is a positive number, such that if you take a point here, you have the fiber, and you have a point here, there is a neighborhood in the circle. This is ZT. That is an element in this set. You have a neighborhood such that all the guys that are into that neighborhood are going to converge exponentially fast, the orbit of them. So this is like a central stable manifold. And this set have a positive measure, alpha, that is a uniform number for each measure of maximal entropy. So that means that you have good manifolds, because the problem with spacing theory is that the size of the manifold is not uniform. So the size can change a lot when you change the point. If you have a point here and you take other point here, this stable manifold could be something like this, and the other manifold could be something smaller. The problem is a problem with size of manifold. Here we have the same size for all the points in this set, and this set is relevant. All the measures of maximal entropy can see this set. So nice. Well, now we want to prove our theorem. The first thing that you have to recall is that all the measures of maximal entropy of the skew product are projecting over a measure of maximal entropy of the base. So you can suppose that by contradiction, that you have infinitely many measures of maximal entropy, and suppose that infinitely many of them are projecting in the same guy, in the same measure of maximal entropy of F. So you have a family that are measure of maximal entropy of the skew product, and they are projecting over the same guy. That is a measure of maximal entropy of the base. So now we can suppose that the Lyapunov exponent is always the same, negative. You can say that it's positive, at the end is the same proof, but suppose that is negative. So we have this set with measure greater than alpha. We also can take the regular point of a measure. When we have ergodic measure, we have the regular points. Regular points are points such that the limit is converging the weak topology to the ergodic measure. This set is good because this set are such that if you have two ergodic measures, the intersection is empty and they have total measure. So call this set the set of the lemma of lambda, and define a new lambda like lambda intersection, lambda end like lambda intersection the regular points. This set have measure equal to alpha, and so when you project over the manifold, as this guy have positive measure uniform, you are going to find intersection. This is one projection, and you take the other one. You are going to find this intersection. And at the same time, if you have a R that is uniform, if you take a lot of number and end number, you are going to find 2 points that are close. R over 4 close. And so the proof is project a lot of measures, find an intersection, a lot of intersection as big as you want to guarantee that you have 2 points that are so close. And so now you have 2 points in this set lambda that are close, and if they are so close, they are in the same stable manifold. They guarantee this property. That means that these two guys have the same future. If they have the same future, they have the same limit. This limit is the same. But they have the same destiny. But that is impossible because they come from different ergodic measures. They are married with other people. They can't be together in the future. So they come from different ergodic measures, but they are converging for the same. That is a contradiction. And the contradiction comes because you are supposing that you have infinitely many measures of maximal length. So this is a reason for why stable manifolds are important in how you can use them to prove that you have infinitely many measures of maximal length. So thank you.